Welcome to another video for chemistry. In this video we're going to be discussing valence electrons and how they determine element behavior. So the periodic table and main group chemistry. So we're going to be looking at the main groups in the periodic table. These elements are organized into different blocks on the periodic table, and we'll highlight those different blocks. And before we continue, let's highlight the different objectives that we want to cover in this video. First of all, why do elements in the same group have similar chemical properties? And what are the four blocks of the periodic table? So like a house number is not enough to deliver a letter to the correct address. More information such as a street name, a city, a state is necessary to deliver a letter. Similarly, chemical elements are identified according to details about the arrangement of their electrons. So the number of electrons and where those electrons are arranged are like giving the address or the exact location of an element on the periodic table. So this next series of videos will help us in using the electrons of an element to identify its location and behavior. So electrons in the highest principal energy level, or the electrons that are furthest away from the positive charged nucleus, these are the valence electrons. They are the furthest away. They are most unstable and likely to react with a neighbor element. How that element reacts depends on how many valence electrons it has. Elements with the same amount of electrons, valence electrons that is, will behave in similar ways with other elements. So let's take an example, sodium here. Sodium has 11 electrons, and I know this because of the atomic number 11. And typically in a neutrally charged element, the number of protons, which again I get from the atomic number, the number of protons will equal the number of electrons. Okay, and again, this is in a neutrally charged element. So the other way I can do it is I can just count down the line along the periodic table and finally get to 11 and know that I have 11 electrons. So sodium has 11 protons, and those protons are located in the nucleus, and of course there's also neutrons there, but just for simplicity's sake I just drew in the protons. And the protons are a positively charged particle, and again this is neutrally charged, so that means there's 11 electrons also. Now the question is how do we organize these electrons? Where are they located in the atom? These electrons are actually orbiting around the nucleus. So that positive nucleus, that positive charge, keeps the negatively charged electrons in a specific orbit. Now, actually, let me go back just a step there. It's actually not a specific orbit per se. This diagram here is a bit inaccurate in the sense that the electrons don't have one single path that they follow along the nucleus. They actually they do inhabit a specific orbit, but they don't inhabit a specific or I don't mean orbit, I mean orbital. They inhabit a specific orbital, but they don't inhabit a specific orbit. They actually float around so fast and are in so many locations that it would be more accurately to call this an electron cloud. Okay, meaning that these electrons go around the nucleus so fast and they're in so many different locations that they give the appearance of a cloud rather than a single orbit. Okay, and in fact also they happen to travel so fast that it could almost be said that they are in more than one place at the same time. So electrons occupy different levels from the nucleus, different orbitals. We call these energy levels or orbitals. So just to give an example of how we diagram or how we illustrate the location or how we find the valence electrons of an element, here I have my nucleus of a sodium atom, and I have 11 electrons. So in that first energy level, in the very first, the circle here is representing the first energy level, I can fit a maximum of 2 electrons. Okay, so that's 2 electrons. After I filled in that first most inner circle, or most inner energy level, I can draw another outer concentric circle. And the following concentric circles can fit a maximum of 8 valence electrons. So I would put them in on the furthest points. So I have 3, 4, 5, 6. And again, I have 11 electrons, so I still have 5 more to count. So that's 7, 8, 9, 10. And now that I've filled in my second level, a maximum of 8 electrons, I can draw in a third concentric circle. And I have 1 electron left, and there's my 11th. Now, this 11th electron is what I would call the valence electron. This is the outermost electron. This is the one that's furthest away from the nucleus. That's my valence electron. This is the one that will determine the behavior of this element, because that is the electron that will be involved in reacting with another element, whatever element that might be. Now here's the thing about sodium. So sodium, you'll notice here, is in group 1. All of these elements here in group 1 have 1 valence electron. So they're kind of like, there's a reason why they call these groups, they also call them family groups. So they call them family groups because they have similar behavior, kind of like a family unit would. I know, of course, there's always exceptions and not everybody acts the same, but just for our example's sake, in chemistry, these groups have very similar chemical behaviors. And the reason why is because they all have that 1 valence electron. So I'm going to play a little video here for you so you can actually see how these elements would react with other elements. Now, some of these reactions we will actually do in class as well. So, but some of them we can't because either these elements are very scarce and super expensive, and they can be very dangerous. But elements like sodium and hydrogen, for example, will definitely, and potassium, you'll get to see in class. Okay, so here's a video.
Whether you've left school or you're still at school, you can appreciate the sheer fun and mayhem that chemistry can be. There's so much to it. Bunsen burners, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium. And you may, under very strict scientific control, have witnessed potassium mixed with water. But the odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, mate, present.
Oh, thank you very much.
These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkali metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody. This one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone. Yes!
Wow.
That is more like it. Only on Brainiac do you get that kind of science. But I believe we can go one better. There is one more alkali metal we can legally use.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty, could go off at any time.
And that's it.
Oh, yes.
Brilliant. I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave you to it. Good luck.
Thank you.
OK, John, go for it.
Warning, 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 extreme danger, clear the area.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does. Magnificent. And I think that concludes today's experiment. There is, I should say, one more, even more reactive metal francium, but for some reason they wouldn't let us have any of that. Still, there you go. Today's lesson:
Never mixed alkali metals with water.
Well, I hope you found that video interesting. Now let's move on to John Newland. John Newland actually discovered this pattern of chemical behavior on the periodic table. He called this pattern the law of octaves. Okay, so every 8 elements, he noticed that the pattern of behavior would repeat itself. And you can actually see this in the periodic table, in the modern periodic table, just like we mentioned earlier with period number 1, or group number 1, sorry. All of these elements have 1 valence electron, so their behavior is very similar to each other. And just like you noticed on the video, so you saw lithium and water, potassium, and rubidium and cesium, and you notice that as you go down the line, this behavior actually gets more and more exaggerated, and that's why francium or francium you did not see, because it's an incredibly rare element and it's also very explosive. So you know, maybe in a military base or something you'll see that. So in the second group you have 2 valence electrons, and all these elements have similar behaviors also. Okay, and then we move on to the other main group elements. You have 3 valence electrons in this group, 4 valence electrons, 5, 6, 7, and then finally 8 valence electrons. Now each of these groups has a certain set of behaviors based off of the fact that they have, based off of the number of valence electrons that they have. Okay, so let's take a look at some of these behaviors. Nitrogen, for example, has 5 valence electrons. So let's actually see that and diagram this. So you have nitrogen with 5 protons. So that means it has 5 valence electrons. And remember, in the first group you have a maximum of 2 that you can fit in. And so then we can make another circle, another concentric circle, and fill in the rest of the electrons that we have. So that would be 3, 4, 5, 6, 7, and then that would be it. It has 7 total electrons. 2 of them that go into the first inner circle, the inner core electrons, and then the last 5 electrons go on the outermost shell. So these are the 5 valence electrons that will be combining with other elements to make a reaction. Okay. So nitrogen and all the elements below it, phosphorus, arsenic, antimony, and bismuth, they all have similar chemical behaviors based off of the number of electrons they have on the outermost shell. So these elements that I have highlighted here, these are elements that also have a similar behavior because of how they share electrons. And that's the thing, they actually do share electrons. They don't take the electrons away from another element, or they don't give away electrons to another element. These elements make what's called a covalent bond. Okay, so these covalent bonds are where you share electrons. These are organic. They make organic compounds. Okay, so all the the cells, muscles, tissues, stuff like that we're made out of are made from primarily these elements that I have highlighted. And then you have halogens, which have 7 valence electrons. I mentioned before that the elements that are made out of, the elements that make organic compounds, they tend to share electrons. Halogens have 7 valence electrons. And I hope you remember that I mentioned before that in the outer circles you have a maximum of 8 electrons. So the fact that these have 7 valence electrons says that they have 1 more electron to get. So these elements are very electronegative. They have a high electron affinity, okay? That means they want that last electron to fill their shell. So they're more likely to take an electron away from another element than they are to give any away, because of the fact that they're only 1 short. In fact, these elements tend to make bonds with the elements from group 1 and group 2, okay? Your alkaline metals and alkaline earth metals. These alkaline metals and alkaline earth metals, these elements in group 1 have 1 valence electron and 2 valence electrons. So if I have 1 valence electron, that means I need 7 more, and if I have 2, that means I need 6 more. So these elements in these groups tend to give those electrons away. It's a lot easier for them to give the electron away than it is for them to gain the 6 or 7 that they need. And these elements on the other side, the halogens, they are more than happy to take that electron away from these alkaline metals and alkaline earth metals. Okay, so they tend to make bonds with each other, and these bonds are called ionic bonds. They don't share electrons. These elements strip the electrons away, and these elements give them away. Okay, and that's an ionic bond. So the noble gases, just think noble. Noble thinks snooty, snobby. They don't react with anything because they have all the electrons they need. All their valence shells are full, so they very, very rarely make a reaction with any element. Okay, so they have a full valence shell. Now, an interesting thing happens with these elements when you run electricity through them. These electrons get excited and they jump extra energy levels or empty orbital shells. So they gain electrons, they gain energy, and these electrons get excited. And when they release that energy, when they jump back down to other energy levels, they release the energy via light, and you get these really interesting light signatures from these noble gases. Now, this particular concept we'll discuss in another video when we talk about the energy levels that these electrons jump. So this video discussed the main group elements, the ones that I have highlighted right here. Okay, and again, remember each group here has a specific number of electrons on its outermost shell. And those electrons, these valence electrons on the outermost shell, determine the behavior of these elements as they combine with other elements in the periodic table. And that concludes our video for valence electrons and the element behavior. Good luck in your studying.